Still in trig, I imagine? Okay. I'm ready. You can see my screen, right? Okay, hold on. I'm almost ready. I keep forgetting always to get really ready. I got to do this. Okay, now I'm ready. You gonna verbalize some problems? Okay. I don't even know what that means, but what specifically is the problem? Do they give you a matrix to start with? Is it a 3 by 3? Is it okay? It's a 3 by 3. Let's go left to right. Okay. Okay. What do they mean by just find the determinant? Don't know what that means. I can figure out how to figure out the determinant. I don't know what it means by expanding it about its minors. Uh-huh. Uh-huh. Gotcha. Okay, that's what they mean by the minors. Because, yeah, I remember reading the other day that a 3 by 3 is just a collection of 4 different 2 by 2s. And actually more than 4. So when they say expand it, they want us to expand it, the 2 by 2s? Okay. Here, let's see if I can. Is this what we're talking about? So the determinant of 2 equals minus 2 minus 0. Okay. Right? Okay. Row 2, column 1. So now we're looking at this matrix. 4, 3, 6 minus 2, correct? Okay. And we're just going to go through all 9 numbers that way? Just column 1. Okay. So what's the determinant of this? Okay. And then the last one is going to be around 5, right? So we're looking at 4. Go ahead. What's... Mm-hmm. plus 0 times? Okay. What are you going to do with those three numbers? Do you add them together? Okay. Uh-huh. All right, hold on. You've lost me. I've never done this with these matrices. Maybe in college, but not lately. This is something that I don't run into very much. Let me see if I can find it in this little more advanced book that I have. Precalculus matrix, Algebra 787. I don't think I have ever come across this. Does this have anything to do with row echelon? Okay, this is totally different. Hold on, let me just go through here and see if I can find any problems in my book where they expanded about its minors. In other words, maybe. No, hold on. No. Got a lot of problems about solving simultaneous equations, but nothing about what you're doing. Maybe here. Hold on. Finally to the determinant parts. Rule. Find the minors of a 3 by 3 determinant. Okay. Wow. In 10 years, you are the first one to get to this part of the book. And looks relatively complicated. Okay. I see what's going on. So you take 2 times the determinant of the minor, correct? So that's the first step, is 2 times the determinant, or times minus 2. And then I'm going to subtract, not add, the second column, which is 4 times, now we haven't done this determinant. This determinant is going to be different. In other words, we only worked on the first column, and the second term is the second column. Hold on a minute, let me just read what it's talking about here. Get it? One, 2. This is pretty complicated stuff, Garrison. I can barely follow it. But if you gave me 15 minutes, I could figure it out and how to proceed. This is really I'm not even sure what the purpose of all of this is, what it accomplishes. In other words, I'm staring at a book that has a bunch of A11, A21, A31, and then A12, A22, A32, and so I'm just looking at all these letters here. It's hard to figure out. Comes right before Cramer's rule for 3 equations containing 3 variables. Yeah, there's like 2 pages, 1, 2, 3 pages of this, finding the minors of a 3 by 3 determinant. Is there anything else you have that we can work on and let me brush up on this before I attempt to tutor you on it? If you do, let's do it. I mean, we can always work on this at a different time. And this is one of those, I mean, you have really no way of knowing that you're on the cutting edge of matrices here. Like I said, you're the first student in 10 years that has got into these minors, such that I wasn't even familiar with the term. What's the other stuff you can work on? Is it trig? Well, let's work on something that I can help you with. I can help you with this, but you're going to need to give me a half hour, an hour for me to review it and figure it out. You know, enough that I can tutor it. Well, it depends. No, we can do anything you want as long as I know how to do it. Yep, those are fine. Okay. Let me tell you the next term. Oh, stop for a moment. What's the next? Well, I was going to tell you the next term. In other words, the numerators are advancing by 1. The denominators are doubling each time. So the next term is going to be 7 over 32. ... Okay, well, what do they need you to do here? Come up with a more general formula? Okay. Yeah. Well, does it even converge is the thing. Because the first thing you kind of have to determine about series is whether they converge or not. Familiar with that term? Sigma? Okay, so they're dealing with this in this material here? Okay, so we need it to go from some number to infinity, because it's an infinite series. And we need the first term. Let me think about this for a second. Let's see, if n's going to go from 1, well, let's let n go from 2. So what do we have? We have n plus 1 all over n squared. Now, first of all, do you understand that? Hold on. No, I didn't write it correctly because the first term would have a 4. Let's see, the denominator's got to be what? The denominator's got to be n plus 1 squared. Huh. And n is going to start at 1. You can have these things start anywhere. And this becomes n plus 2. Now, based on what I've circled, tell me the first term of the series. Don't look at the series above. Just substitute n equals 1. What's the first term? I still don't have it right. No, hold on. That's not correct. It does not give us the, yeah, it gives us 3 over 4. So how am I going to get 3 over 2? And then square it. Let's see. What do I need this to be? Square root of n? I think so. Square root. No? N squared. Huh. Plus 1. No. About down here. There. That gives us the first proper term, doesn't it? Doesn't give us a second proper term. The second term is going to be 5. These are always a little tricky to convert a series to sigma notation. The reason you do that is because you can usually figure out what this would evaluate to. But it's awfully tricky to even figure it out. Let's see. There's various ways to get 3 in the numerator. The only way I can think of to get 2 in the denominator what if you had this? And then get 4 as n advances 1. So n plus 1 works for the first term, but it doesn't work for the second term. This has got to be n squared, or something close to that. And even after I get it in sigma notation, I'm not sure. Why are you doing this problem? This is, oh, okay, now I get it. Think. Whoops. Oops, hold on a second. Yeah, I just had another thought as to how we can do this problem, I think. Yeah, and okay, so here's what I'm seeing. I'm seeing an arithmetic series divided by a geometric series. Now, we have formulas for giving us the sum of an arithmetic series, and we have formulas for giving us the sum of a geometric series. But I don't know if we can do a formula for an arithmetic term by term divided by a geometric. Series of fascinating things. It's hard to even imagine that when you take that out to infinity, that it doesn't go to infinity, right? In other words, you're always adding a positive number. It's just getting smaller and smaller and smaller. So it's a convergent series. Now that is the secret right there. The formula. Hold on, let me find these. Finding the sum of a sequence. Okay. I think this is going to answer my problem. Maybe. No. I believe we are going to have to write it in terms of n. From what I can tell, the question is that's not that easy to do. This is an infinite series, right? Okay. In other words, it didn't end at 6 over 16. Okay. It just occurred to me how we can write this. Oh no, it's okay. It's 2 to the n minus 1 with n beginning at 2. Yeah, there you go. That gets the denominator. Notice why that produces the denominator. And the numerator is just n plus 1. There's our series right there. Give me the first term of that series. Three halves. Can you hear me? Okay. Second term, n goes to 3. So the numerator becomes 4. And the denominator becomes 2 squared. The third term, n goes to 4. The numerator becomes 5. And the denominator becomes 2 cubed. So that's our series for sure. Now the question is how to evaluate that. In other words, it's hard enough just finding that, figuring it out. Now let's see. There are some things I can do here algebraically. And that is, I can turn this thing into n over 2 to the n minus 1 plus 1 over 2 to the n minus 1. So there's another way to express that series, and I would need summation marks in front of each. In other words, the sigma of the sum is the sum of the sigmas. You know what? Here, let me just rewrite this so it's not so confusing. We still aren't quite ready to figure out what that sum is, but it's worth knowing some of this other stuff also. First of all, that expression. Now that we've proven that's correct, that's the same. I can split this into two fractions. Okay, the first fraction is n over the denominator. Second fraction is 1 over that denominator. Notice that if I added those two terms together, I've got a common denominator, and I would get n plus 1 over 2 to the n minus 1. Okay, So this right there is the same as, let me write it up top. And the reason this might be better is because now we are looking at simpler series to evaluate. Okay. And so you get that this here is equal to that, right? Okay, let's see. So, it sounds like your audio might have come on. Just heard a big beep on my, which is usually the noise I hear when somebody's audio is there. Let's talk about this series here. Okay? That is the following series. Now, there's a relatively easy way to figure out what that series goes to. And this is how you do it. You draw a square. That represents 1. The first term takes all of that. That represents 1/2. Divided in half again, that represents 1/4. So what I've scribbled down in the square represents those first two terms, 1/2 plus 1/4. With me? Now the 1/8 is I take that and divide it in half, and I add 1/8. And then I add a 16th. Then I add a 32nd. Tell me what that thing's going to approach by the time you get to infinity. 1. Remember, the whole thing is 1. When you add 1/2 to 1/4 to 1/8 to 1/16 to infinity, all you're doing is each of those last terms, notice I'm just splitting up. I never do fill up the square. But that series is said to sum to 1. And it doesn't ever go beyond this square, which I'm calling 1. In other words, it never goes to 1.1, it never goes to 1.2, never goes to 2. It just approaches 1. So this series right there is equal to 1. Okay? Let's look at the other series. What is this other series? That is starts at 2 over 2 plus 3 over 2 squared plus 4 over 8 plus 5 over 16 I know this series goes to 1. And this is a very similar series. It's just got different numerators. The bottom is still going 2, 4, 8, 16. It's just that the numerators aren't 1. They're 2, 3, 4, 5. This was actually the series. No, the first term of your series was 3/2. So this is a slightly different series. This series clearly goes to 1 and more, right? The first two terms are 1 3/4. Do you have an answer on this? If you have it, I'll bet it's close to 4, yeah. No, it's more. It is 4? Okay, because what we have here, if I expand this series out on the left, I've got 1 plus 3/4 plus 1/2 plus 5/16 plus 6/32. And we can see right away that that goes to 2 1/4. I know this one goes to 1. So if I had to make a reasonable guess, it would be 4, right? In other words, this entire series goes to 1. Just the first 3 terms of that series goes to 2 1/4. So that's already 3 1/4. And then all of the rest of those small little tiny pieces must add to 3/4. But I don't know how to prove it. I don't know how to find the sum of that. It's easy enough to find the sum of that. This one on the left is the toughie. Yeah, hold on. We're getting some hard problems here. Properties of sequences. Aha. Oh, are you allowed to use a calculator here? Are you allowed to use your calculator? I think that's the way you're going to have to. That's the only way we're going to be able to do it. Is with a calculator. Well, here's the thing. A calculator has a function on there that is the sum of a sequence. Okay, here, let me write the formula for it. Because I don't want to erase everything. We may need the top row. But in other words, this may be a problem that they're expecting you to do on your calculator, not manually. Is that possible? It could be problematic. I've got the most advanced pre-calc book I have. Doesn't show you how to do this one by hand, but it does show you how to do it using a graphing calculator. And here is the fact. I can put this into Wolfram Alpha. I'll do it in just a moment here. Are you familiar? Have I used Wolfram Alpha with you before? Okay. An example would be this one. Oops. 1, 5, comma, and another 1. So that's what you'd put into the calculator. And in our case, it's going to be, we know the sum on the right already. So if we want to figure out the sum on the left, I think we'd have to put it in like this. Comma, n, comma, 151. See, I would normally say that this is going to go from 2 to infinity. That, if I put that into Wolfram Alpha, that should give us the number 3. Let's see if it does. I'm going to have to do it this way. Love to be able to do this manually, but again, I don't know how. I can do some of them manually, but not a ratio, you know. Nicer. If we're going to do some of these problems that you start at a lower level. You know why I say that? Whenever you're doing mathematics, you don't want to start at the hardest level. It'd be like learning how to ski by starting on the expert slopes. You always begin on the beginner slopes. And when you get good enough to handle those, you go to the medium slopes. Well, you're starting off with the toughest of the toughest on some of these. Here, I'm going to put it in exactly as I wrote it. Let's see what it gives us. I need a parentheses. I need to define my sum, which, oh man, it's not going to be easy to do here. It's n divided, what was the bottom? N minus, no, it was 2 to the n minus 1. 2 raised to the n minus 1. Let's see. Comma, the variable, n, comma, 2, comma, infinity. And I probably need extra parentheses right here. I need parentheses around that whole thing. The beauty of Wolfram Alpha is that after I try to put it in with all these parentheses, it's going to show me what I've put in. And your calculator doesn't do that unless you have an Inspire. Nah, it didn't seem to like it this one. No, I didn't get it in there right. Sum of the sequence to infinity. What if I put 100? Let's see, it just didn't like my wording of infinity. I don't have an infinity symbol. Doing it, not even close. This is the formula I'm looking at in my book that shows you how to do it on a graphing utility. The TI-83 actually. I just assumed it would be the same format for the hold on a second. Oh, this might be useful. I'm going to write this on. I'm not getting anywhere with Wolfram Alpha, but I see some other stuff in the book. No, that's all arithmetic. And here's geometric. We've got sums on both of arithmetic and geometric. What we don't have is formulas for finding the sum of yeah, exactly, which is what we're looking at. And here we have the sum of an infinite geometric series. I don't know if that's going to help. It might. I don't know. Let's see. If I write the sum, we definitely have an infinite geometric series. The sum of AR to the K minus 1, they're using K instead of N, where K goes from 1 to infinity, is equal to A over 1 minus R. Now, what is R series? R series is, I'm merely looking for this sum, n over n minus 1 squared. No, I keep doing that. It's hard to remember to put that n in the exponents. 2 to the n minus 1, where n goes from 2, must be n, oh yeah, there was a plus 1. Originally, there was a plus 1 up there. We've separated it out so that now it's not plus 1 anymore, it's just n. Now, let's see, can I use this information? Maybe. In other words, I know what this is. They're telling me right there that it is, R is 1/2. Okay? So that would be A over 1 minus 1/2, or 1/2. If I had an A that was a constant number. I don't. I have an N. In fact, my A is 1. Gosh. I feel like I'm close to seeing the solution. I can't see it. Jesus, you're going to hit me with mathematical induction next, aren't you? Have you had that? Good. That is a hard subject. I'm not getting anywhere in my book here. Finding the sums of these that are... My book is full of formulas for sums of arithmetic sequences or series, and also geometric sequences or series. What it doesn't tell me how to do is a combination of the two. Yeah, I don't know what else to do. I apologize, Garrison, for having to do this, but you're just dealing in areas that I never deal with. Let's try something else. We're close on that one. In other words, and we can see why it's 4. If you said, you bet your life that, make a guess, best guess you could make, I would have guessed 4, because I could see how there is something I would like to point out, just from a matter of interest. This will probably blow you away. We know that that thing goes to 1, right? What do you suppose this one does? Believe it or not, that goes to infinity. This is called convergence. This is called divergence. When you get into calculus, Calc B is all, or Calc 2, is all about infinite series. And the first thing you have to determine about an infinite series is, does it diverge? In other words, if it goes to infinity, we can't answer any more questions about it. You can't find the sum of a series if it diverges. But if it converges, then it'll go to a number and you can actually use that formula to figure out what that thing goes to. I used the graphical representation to show that that went to 1. But it's relatively easy. You're talking about this 1/2 to the n minus 1 power. Okay? And what we're told is that sum is 1 over, well, it's a, which in this case is not 1/2. It's a over r. This is r. Okay? So this would be 1 minus r, which is 1/2. So I would have 1 divided by 1/2, which is 2. But the series I've actually written there, if n starts at 1, then the first term is 1. It's not 1/2. So that's why it's 2 instead of 1. Because the convergent series is actually 1 over 1 plus 1/2 plus 1/4 plus 1/8. Because when n is 1, 1/2 to the 0 power is this number right there, 1. So if I had a convergent series that started from n going to 1 to infinity of this, 1/2 to the n minus 1, my book says that this is equal to a, which in this case is a is that, which is 1, over 1 minus r. And r is the number that's in the parentheses being taken to that exponent. So the first term of this particular series that I've written in blue with the sigma notation is not 1/2, it's 1. Then you go to 1/2, and then you go to 1/4. So you can see why that adds to 2. Okay. It still astounded me that this was convergent and this was not. The bottom one is that I've written in red does not converge, 1/2 plus 1/3. Even though the number keeps getting smaller every time, there is one way to look at it so that you can understand why that does not converge. Notice that if I start with whatever number I start with, the next two terms are greater than that number. Right? 1/3 plus 1/4 is 7/12. And no matter where I look in the sequence, if I wanted to start with that term, the next two terms are greater than that previous term. So one way to see this sequence is, well, it's 1/2 plus those two terms, which is 7/12. And then you can see that that's a number that keeps getting bigger. And you're constantly adding a bigger number to the sequence on to infinity. Well, if you're constantly adding a number that's growing, then obviously it's going to go to infinity. Where the other sequence, that's not true. If I write this sequence, the sum of those two terms is less than that. And in fact, the sum of all of the terms that follow 1/2 is just equal to 1/2, all the way out to infinity. But that's the key understanding of why one is a convergent series and why the other is not. Is that in the convergent series, the next two terms combined are less than that 1/2. Whereas in that divergent series, it goes the other way. So that's kind of an interesting, this is their introduction to calculus, actually, those two series. Yes. Yes. Yeah, although those are just two very specific sequences, or series, I should say. The difference in terminology is a sequence is just a certain number of numbers separated by commas. A series is all of those numbers added together. And then an infinite series is all of the numbers added together, and it goes on out to infinity. And most people, if you said, what's an infinite series do? They're going to say it diverges, because if you're always adding numbers forever, how can that thing not go to infinity? But they don't. They do converge, some of them, like 1/2 plus 1/4 plus 1/8 converges. We just have a few more minutes, don't we? You got anything we can do in 5 minutes that's not college material? Because, okay. 4 and what? Okay. If x is the geometric mean, that's what it means. Yeah. So x squared is equal to 2,000. So x is equal to plus or minus the square root of 2,000. What's the square root of 2,000? That's, now 100 squared is 10,000. So that's not a easy number, right? You can break it down a little bit, but I guess you could take out a 10 and cross off 2 of the zeros. So this is the same as 10 times the square root of 20, which is the same as, we don't need to worry about simplifying it. So the question is that the next term, or so we need to find two numbers that are going to go, in other words, x and y, such that that is a geometric series, right? Okay, I think I can figure out how to do this. So what we need is x times 4, or rather x divided by 4 is the common ratio. And that is the same as y divided by x, which is the same as 500 divided by y. And that should okay, so here's our two equations. We got two variables, okay, working working with this one first gives us x squared equals 4y. And then working with this one over here gives you y squared equals 500x. Now by substitution we should solve for x and y. So, let's see. Well, I don't think it really matters. We can surely solve this by substitution. Let's see. If I solve for y from the first equation, I get y equals x squared over 4. And now if I substitute that into the second equation, I get x squared over 4 squared equals 500x. That has a solution. Okay, that is x to the 4th over 16 equals 500x, which is x to the 4th equals 8,000x. So, yeah, x cubed equals 8,000. So x is 20? Yeah. Perfect. That's 20. Now we know our ratio is 5 to 1. That's got to be 100. There's the two medians right there, 20 and 100. Okay, well, I'm glad you gave me at least one problem I could do, Garrison. I tell you what, I want you, as long as you're dealing with such difficult stuff here, if you could, before every session, just send me a quick email or a text telling me what the subject matter is going to be. Whether it's matrices or, in fact, maybe even a sample problem. Because just knowing the subject matter wouldn't have done me all that much good today, because you're in level 8 out of 10 of that subject matter. So, yeah, I know. I don't know if that's just, you're in Alabama, right? I don't know if that's just the difference in the Alabama curriculum as opposed to Colorado, but like I said, I maybe have seen problems like this where you find the two median, means rather. But those other problems are crazy hard. Well, the matrices aren't crazy hard. It's just I need to review it a little bit. But the best thing you could possibly do is send me, if you have some problems that we're going to be covering, take a picture of it with your camera and send it to my email. Do you know what my email is? Let me write it, because I want you to send it to this email. If you go to my website, that email takes a long time to get to me, whereas this one comes direct. Yeah, write that down or put it in your phone or something. And then next time, it would really help the most if you can send me a picture of the problems we're going to be talking about. Then I can do some research in advance if I don't know how to do them. Doing that research in real time is really tough. Okay, Garrison, I'll let you go, and I will talk to you next Tuesday at same time, 3:30 my time, 4:30 your time. Okay, I'll talk to you later. You too.